This is my final project presentation for STAT 437. The dataset that we are looking at contains variables related to brain anatomy and political views across 90 university students. The variables used throughout this presentation will be amygdala, ACC, orientation, and conservative. We will first investigate the relationship between orientation as it relates to amygdala and ACC. To do so, we will first look at the correlations between orientation and amygdala, and orientation and ACC. After this, we will obtain 95% bootstrapped confidence intervals for both of these correlations using resampling of cases. After doing so, we will then regress conservative on amygdala and ACC using both a logistic regression model and an additive model. To compare these models, we will interpret their calibration plots, interpret the fitted models, obtain in-sample misclassification rates for each model, estimate the general misclassification rates through cross-validation of each model, and we will test whether the logistic model is properly specified when compared to the additive model. We will first look at the scatter plot for orientation versus amygdala. The scatter plot shows no clear linear relationship between the two variables. R gives a correlation of approximately negative 0.2215031, which signifies that there is a weak negative linear relationship between orientation and amygdala. Looking at the line of best fit, we see that it is negative sloped, and thus further signifies a negative relationship between the two variables. We now look at the scatter plot for orientation versus ACC, which shows no clear linear relationship between the two variables. R gives a correlation of 0.2699053, which signifies a weak positive linear relationship between orientation and ACC. The line of best fit has a positive slope, thus further signifying a positive relationship between the two variables. To determine if the correlations are really non-zero, we obtain 95% confidence intervals for these correlations using bootstrapping. The approach we chose was resampling of cases rather than resampling of residuals, as the only assumption we need for resampling of cases is that each data point is an independent observation, where for resampling of residuals, assumptions about the underlying model are needed. As we can see, neither of the 95% confidence intervals overlap with 0, and thus at the 5% significance level, we can say that both correlations are non-zero. We also see that neither correlation is very high when we take the absolute value of the lower and upper bounds respectively. Next, we look at the calibration plots for each model. Both models are calibrated as the lines go through all the circles for both plots. The additive model seems to have the predicted probabilities closer to the actual probabilities than the logistic regression model, although this does not say that the additive model is more calibrated than the logistic regression model. The in-sample deviance for the additive model is lower when we compare it to the logistic regression model. To determine if this difference is statistically significant, we will perform a hypothesis test. R gives us a p-value of approximately 0.27, suggesting that the logistic model has a statistically higher deviance than the additive model. The in-sample misclassification rate for the logistic model is approximately 16.67%, compared to the in-sample misclassification rate for the additive model, which is lower at 14.44%. Thus, the additive model performs better than the logistic model on the in-sample data. To determine which model performs better on out-of-sample data, we will use cross-validation to estimate the generalized misclassification rates for each model. We chose to perform threefold cross-validation to estimate the generalized misclassification rate for each model. And as we can see, the estimated generalized misclassification rate is lower for the logistic model. Thus, the additive model overperformed on the in-sample data, and the predictions used for out-of-sample data are more accurate using the logistic model. Our final conclusions is that the logistic model has a statistically significant higher deviance than the additive model. The additive model has a lower in-sample misclassification rate than the logistic model. The logistic model has a lower estimated generalized misclassification rate than the additive model when estimated by cross-validation. Thus, in conclusion, the logistic model is better for making predictions outside of the data, but has a higher deviance than the additive model.